Welcome to qnawire.
Once again, welcome to a new problem. This time we're still dealing with springs and spring constants. Remember, anytime you're dealing with the spring, you always think about Hooke's law. And the K happens to be what we call the spring constant. If you want to solve for K, you have f over x. So in this problem, we have a massless spring. Okay, we have a massless spring, and then what's going to happen is that they'll split the spring into two parts, so two different parts. So they're saying if you split that spring into two different parts, if the initial spring constant for the single spring was k, and let's call the spring constants for the two different springs, let's call it k1. Let's just call it k1. And from a practical point of view, think about a single spring. You split that into two, and then you try and stretch the smaller pieces. You'll find that it's harder to stretch. Okay, so compared to the original spring, even though you're still applying the same force, so the same force is being applied. If the initial length of this spring was x, then it means that these two new springs will have a length of x over 2 because you're dividing them by 2. So the question becomes, if you do that, what's going to be the spring constant? Like what's going to be the new k that you're dealing with? So again, you start with Hooke's law. This is part A. Hooke's law is kx. So k equals to f over x. But then our x has changed and our k has changed. Now we're not calling it k, but we're calling it k1 for the spring that is split into two. X becomes x over 2 because now you're dealing with half the spring. So this is f over x over 2. You use division. So k1 is going to be, this 2 comes up. It's going to be 2f over x, 2f or over x. But then remember, if you can recall that k was f over x, k was f over x, so we can always change this f over x to our original k. And so our new k1 for half the spring becomes 2 times k because k is the same as f over x. All we're saying is that if you split the spring into two, the new spring constant will be twice as much as the old spring constant. That's what we're saying. The second part of the problem assumes or wants you to have a spring initially with the length of x, and then you split that into three different parts. So it's going to be, x, x3, x over 3, x over 3, and x over 3. So now, initially, f was kx, and then we divide both sides by k. We find a formula for the displacement of the spring. So, or rather, I should backtrack that a little bit. It wasn't solving for x, but I'm solving for k, which is a spring constant. So the original spring constant happens to be k equals to f over x. If you split the spring into three parts, let's call this k2. So f equals to k2 times x over 3. So k2 is a spring constant for each one of these small springs. We're going to divide both sides by x over 3, and this one x over 3. So we end up with k2 being 3f over x. Initially, f over x was our spring constants for the original spring. So we're going to say k2 equals to 3k. All we're saying is that if you split the spring into three different equal parts, your spring constant k2 will be 3 times the original spring constant. So our final solution is k2 equals to 3k. Hope you enjoyed the video. Feel free to share any comments, any questions. Again, This is computations of the spring constant as you change the length of the spring. And it makes sense, when you cut the spring. Imagine if you cut the spring into infinite parts, the spring constant will also be like super huge, difficult to stretch or to compress. This is something you can do at home. You could take a spring, cut it into two, and just see how difficult it becomes as the length of the spring gets smaller. Thank you very much and have a wonderful day. Okay, bye.